Okay, I have started to record the class. So is it okay for us to start now? Right.
Yes,
Thank
Doctor.
you.
Yes,
Welcome. Welcome back to the class. Okay, can we all mute our microphone? All right, thank you so much. So, welcome back to the class. So, today I would like to talk about system identification. I think the first class we have talked about the introduction on adaptive control. So, today maybe I will show you a little bit on how adaptive control require the model of a system to be known, okay, and how is it differ from the actual the normal control system. Okay, so we will talk about system identification. System identification is a modeling technique, okay, where you need to have a data input and output data of a system. So I will talk about it later. All right, I have shared this slide with you, so you can refer to the slide that I've shared with you just now. Okay, so identification, let me hide this. Okay, identification is a method of measuring system transfer function or some equivalent mathematical description from measurement of system with input and output of a system. For example, I have a plant, okay, air conditioning system, for example, or a furnace or automotive system, okay. So I give some input to the system, a disturbance perhaps to the system, okay, and then we check what is the response of the system. Okay, so this is input. So normally a control system, as you already know, is represented by block diagram like this, isn't it? So there's a block and there's an arrowhead showing inside the block. This is the input to the system, and then there's an arrowhead to show output of the system going out of the block, so it's showing the output of the system. Okay, so using the input and the output of the system, we can actually identify what is the transfer function, okay, by using tools or techniques. So there are several techniques, okay. So for example, identification can be in a form of analysis and simulation. So why do we need to identify a model? Okay, so I give an example here. If you remember, okay, Halley in 1704, you can maybe Google this information later on. Okay, back in 1704, this is a very long time ago. Okay, what happened is that this person by the name of Halley, he computed an orbit, okay, of a comet, okay, and this comet is actually predicted, okay, to come back to the our system, our uh, close to our earth, so that it can actually be seen very close to the earth, right? So this comet is called Halley's comet, okay, is very well known. All right, and what happened with the Halley comet, this is being computed back in 1704, and it predicted to come back around 1980s, okay. And what happened, it does come back. All right, so Halley's comet is the very famous comet. It is predicted to come back every 75 years, and it's actually possible for us to see it, okay, at least twice in our lifetime. So I've seen it in 1986. I'm sure some of you have seen it, or at least we know about it because people take pictures and post it, okay. So it is also projected to come back again in 2061. So this is actually a prediction, okay. How do they predict? It's actually quite miracle, okay, back in 1704, when they can predict by utilizing a very limited technology back then. But now we can predict more, is it? We have been predicting a lot of things, okay. For example, if you remember Planet X, do you know about Planet X? Okay, we predict that there will be a planet, okay, will emerge in our solar system. We can see it by 2018, I think, if I'm not if I remember well. They have predicted maybe 20 years ago, but until now we have not seen it yet, okay. So maybe it will come later. All right, so this is a kind of prediction that we have, okay. But there's a lot of other prediction that happen every day in your life, isn't it? For example, today we forecast we predict the weather, we do weather forecasting. Okay, so there's a lot of prediction. So this is how do they predict? They actually do this by identifying the model of the system. So by utilizing a lot of data, by getting a lot of data, we observe the pattern of the system. How does the input actually shape the output of the system? So this is how we do prediction. So prediction is is a form of identification. Okay, how about today? What happened in 2020? The world pandemic. So have we predicted it? So if you do some research, okay, there are many people who have actually predicted that world pandemic will happen. Okay, after 2018. So they predicted it will happen again because it's happening every beginning of a century normally. Okay, so supposed to happen maybe in 2000, but now it's happening in 2020. So this is actually something not unexpected. It is expected, but of course it's unwanted. Okay, but it is expected. Why? Because of we have seen the pattern from the previous. Okay, but of course we have limited knowledge about it. We can only predict that it's going to happen, so we can make a very active precaution. Okay, what to do. But of course we have to it is in our limited knowledge. Okay, we are only humans, so our knowledge is very limited. Okay, but we can learn from the past experience on how to overcome it or on how to deal with it. Okay, so this is a good thing about identification and prediction. Our prediction might not be correct, but we can identify the model so that when we can actually tell the system, all right, we can actually tell how can the system we can take care of the system later on when things happen. For example, when you predict the weather forecast, when you forecast the weather, you predict that it's going to be raining, isn't it? So for example, today, maybe 7 days ago, you know already the weather forecast today is going to be raining, so you should prepare. So maybe you can bring your raincoat, you can bring your umbrella, okay, or you can maybe work from home rather going to office. Okay, so this is actually something how to deal with it. Maybe you cannot control it. If it's raining, then it's going to be raining. Okay, but it's okay. But we can actually do something to overcome this matter, to solve our problem. Bring umbrella, bring raincoat so that you don't get wet. Okay, so this is the beautiful thing about identification. All right, so some example of identification. All right, in terms of modeling of a system, in terms of engineering, for example, okay, identification is very close related to modeling the problems. Okay, why do we need to model the problem? Because we need to maybe control the system, so we need to actually know how the plant behave. Okay, so modeling is more like to find out how does the plant behave so that we can control it later on. Okay, so in terms of engineering, identification is actually obtaining the mathematical description of the system. All right, there are two solutions for modeling. One is analytical modeling. So what happened with analytical modeling is when we split the system into several subsystems, okay, and then we found out what is the mathematics behind the subsystem, and then we can actually then come back and join the system together and try to solve the overall problem. For example, when we talk about automotive system, a car, for example, okay, so when you have a car, you can split the car into several subsystems. You cannot model the car as a whole. Okay, there are a lot of systems that built together, joined together, integrated to become a complete automotive system. Okay, so what happened is that you're going to split the system into several subsystems. For example, the suspension system of the car, the engine, how the engine working with the gear and the steering wheel, for example, okay, and then the air conditioning of the car, for example, and then the comfort level, and there are a lot of things inside it. Okay, so inside a car, there are several subsystems. So what happens is that when you want to study, you have to split it into a very simple, a very specific problem so that we can actually control it. I will show you later on in this class. For example, a very simple subsystem of a car, which is the suspension system of a car. So when we do this, we're going to split the suspension system of a car. Maybe there are 4 wheels, isn't it? So there are 4 suspension system in a car. To model the whole car, maybe is too big, too huge. So what we do is we divide it into 4 subsystem of the suspension system. We call it a quarter car. So quarter car is the whole suspension system, but we split it into 4 parts so that we just take care of one of it. So let's have a look of the suspension system of a car. All right, I'm sorry about the pictures. It looks a bit okay when I edit it, but when we run it, it become like this. Okay, so just bear with me. Okay, this is an example of a quarter car system. All right, so you have your wheel where you present your wheel as M1 here, the wheel of the car. All right, and then you have the mass of the body of the car, which is in this case a quarter of the mass, is represented by M2. Okay, can you see, hang on, let me just give you some laser pointer. All right, so this is M1. Okay, M1 is actually representing the wheel of the car. And then you have your suspension system, which a simple passive suspension system, which is a simple damper and a spring representing the passive suspension system of the car. And then we have our body of a car. Okay, this body unsprung mass of the car is of course not the whole mass of a car, but the quarter. So if the whole mass of a car is 200 kilograms, we can then just divide it into 4. So this is just what, about 50 kilograms. Okay, quarter of the mass of a car. All right, so what happened is that there's a force here. I will actually do a little bit of editing later on. This is a force, okay? There's a force here, Ft, all right? It's coming from the profile of the road profile, okay? So this is a round circle here. I put here is just like a wheel of the car where you represent it as a spring, okay? Because the wheel of the car is a sprung mass, so it is actually very looking like a spring actually. All right, okay, so what happened is that when you drive your car will undergo a road profile. So this is the road profile, and then if it's a very smooth profile, of course the force here is a very smooth, maybe just a straight line. But when your car undergo hump and also hole, all right, so what happened is that this force will actually push your wheel to go up and down. All right, so when your wheel goes up and down, of course your suspension system here will also move up and down, and then your mass of your car will also move up and down. Okay, so what happened is that for thinking about the comfort of the car, of course you want your displacement x2 to remain the same no matter what happened with the road profile or what happened with this displacement x1, but displacement at x2 must remain the same so that the car does not have the feeling of the bumping of the bumpy road. Okay, so you want to be very comfortable inside your car, right? So you want this M2 or x2 rather to stay on the on a very fixed fixed set point. Okay, so for example, if I put the set point here, x2 to the ground, maybe I can set it about, I don't know, about 200 millimeter, for example. 200 millimeter is about 20 centimeter. So whatever road profile that I have, if it's bumping, okay, what happened is that I want that 20 centimeter to remain the same. Okay, so it doesn't change. Okay, so that my car will be very smooth, like driving an Audi, for example. Okay, but of course if you drive a very rugged construction car, for example, four-wheel drive, not four-wheel drive, for like a truck, for example, okay, of course, the body will feel all this bumping, okay? So now, in order for you to model the suspension system of this car, okay, you need to first define what is the input and output of the system. Okay, then you need to draw the free body diagram, and then you're going to derive the mathematical equations, and then later on you draw the block based on the mathematical equation. Okay, in this case, how do you define input and output of the system? That is actually quite straightforward. When you want to define the input and output of the system, the input must be what is the desired level, output that you want for your suspension system. In this case, just how I mentioned about X2, isn't it? I want X2 to be fixed, okay? No matter what happened with the disturbance, I want X2 to remain the same, okay? So I can put X2 as my output of the system, okay? And also input, reference input of the system. But in this case, when you want to model the system, this input must be what is it that actually make my system move, okay? What is it that actually disturb my system? So in this case, the disturbance of the system is my force here, F2, F here, Ft, okay? So this force is actually the one that actually disturb the system, that make the system move. And when I have that input, I want my X2 to be remain the same, okay? So this is how you define input and output. So then you know what is it that you can control, okay? Maybe you cannot control the road profile, so you need to control X2. So X2 is the desired input, not the input, but the desired input. I will show you the difference between desired input and input later on, okay? So what to do about this? Let me just, you have this slide, isn't it? So let me just draw hang on, show you how to draw the block diagram out of this, okay? I'm going to unshare this, and then I'm going to, hang on, let me just stop sharing. And then I'm going to share you my notes, okay? All right, can you see my notes? Can you see that?
Yes.
Yes, sir.
All right, so you have the suspension system just now, isn't it? So what happened with this suspension system? Okay, so you have M2. So I'm gonna help you on solving the mathematical drawing of the system. Okay, so you have M2, and then there's a damper, and then there's a spring, okay, and then M1. So you know now M2 is the body of your car, M1 is actually the spring of your wheel, isn't it? The wheel, okay? So this is your road profile. Oops. So of course, road profile is not a straight line, isn't it? Normally you drive on a ramp, on the hump, and there's a bump and all, okay? So what happened to your car? Your car will go up and down based on this. Okay, so I'll put here force. This is force that disturbing your suspension system, okay? When the force disturb your suspension system, what happened is that your spring, you have spring here K1, this is K2, this is C, and then when your force push up or going down the hole, okay, your M1 will move according to X1, isn't it? Okay, so that X1 will happen on the wheel of your car. You need to imagine this, okay, guys? Okay, right. So what happened is that then M1, when it move up and down, it will also reflect to your damper on your spring K2, and then the spring K2 and damper also will move up and down, and that will actually move your M2 as well. M2 is the body of your car. All right, so M2 also will move up and down. Okay, so now in control system, we want to control X2. We do not want X2 to be moving up and down. Okay, we want it to be set, maybe the response remain the same, and we can put that as a reference signal. Okay, so what is the input to when we want to draw the block of the system? I'm sure you still remember how to do this, okay? When you want to draw the block of the system, you need to draw the free body diagram of the system first, and then you need to define the input and output of the system first, and then you need to draw the free body diagram. In this case, input of the suspension system is force, okay, Ft, and then the output of my suspension system is, what is it that I want to control? Okay, in this case, I want to control X2, right? Why? Because I don't want my car to move up and down, the body of my car to move up and down. Of course, the wheel will keep, moving up and down because of the road disturbance, all right? Okay, now, when I have the input and output, I need to draw the free body diagram of my system. So to draw free body diagram of a system, I'm sure you still remember, is you split the mass into two parts, isn't it? M1 and M2. And then normally what I do is I will do the mass with external forces first. So let's do that. This is M1. So I have external forces F. So this is my free body diagram, okay guys? Okay, then when I know when I push the mass go up, I know the spring K1, it doesn't like to change, isn't it? It want to go back to the original position. So K1 Fs1, force due to the spring 1, it like to come down. Okay, you want to go back to the original position. Okay, similarly, when I push my mass going up, the damper C there, okay, the force due to the damper will move up, okay? The damper doesn't like to move up. The damper want to remain on the original position. So FD will go downward. I hope you still remember this, okay? So all damper springs, they don't like to be changed, isn't it? So when there's something disturbing, for example, when something pushing it up, it will actually push it back down. It want to resist the motion, okay? So the damper will push, the force due to the damper will push it down. Similarly, for spring 2, it will also push it down Fs2. So this is a free body diagram on M1. Okay, so for M2, it's going to have the, okay, I'm going to draw M2 now here. For M2, it's going to have the reaction of FD and FS1, okay, equal and opposite force on FD and FS, sorry, not FS1, FS2. FD, since the M1, for M1, FD and FS2 is going down. For M2, the FD and FS2 will go up. Why? Because of Newton's law, okay, it will actually have equal and opposite direction force, okay? So FD and FS2 here, all right? So this is the only forces happen on M2, all right? Okay, so if you have any question on this, maybe I'll give you more example later on for you to try to do your free body diagram, to do a little bit of a study. Okay, I know you've done this before, but you need to revise a little bit. This is not part of adaptive control, and unfortunately, this is basic control system. Okay. All right, so what happened is that when I have the free body diagram, I'm going to write it equals to my kinetic diagram, isn't it? So kinetic diagram says that M1, it want to go up. Okay, why? Because I have the force pushing it up. For example, I'm just taking, assuming the force is going up. So force Fm1, it want to goes up. Okay. All right, and then similarly for my kinetic diagram Fm2, for mass 2, Fm2, it also wanted to go up. Fm2. All right, so once I have the free body diagram, I need to write all the mathematics that relate to all my devices here. I have here 2 spring, 2 mass, and 1 damper. So I'm going to have equation for every one of the spring, the damper, and every one of the masses. Okay, and then I will have, so in that case, I will have 5 equation because I have 2 spring, 2 mass and 1 damper. So I have 5 equation on that. And then I'm going to have the summation of forces due to mass 1, 1 equation. And then summation of forces due to mass 2, 1 equation. So I will have 7 equation. Okay, so I repeat that. For this block diagram, for this suspension system, I have I have 2 spring, 1 damper, and 2 mass. So I'm going to have 5 equation representing this. And then I will have additional equation from my free body diagram just now. One is actually for the summation of forces of M1. Another one is summation of forces on M2. Okay, so I will have in total 7 equation. Let's write that equation. Okay, for spring 1. Okay, when you look at the system here for spring 1, what happened is that the spring is actually pushed up. Okay, so the spring is force is equals to kx, and in this case the x is x1. So I have force of spring 1 k1 x1. That's very straightforward. Okay, so 1 force due to spring 1 is equals to k1 x1. All right. And then I have force due to spring 2. Okay, spring 2 a little bit different than FS1. Why? Because it moves into location here, isn't it? You have a motion in due to x1 and also due to x2, because the two end of the spring able to move. Okay, so what happened first? Let's have a look what happened first. First, your mass 1, when it being pushed by your force, your mass 1 will move up. Okay, when your mass 1 move up, your spring 2 will be compressed. Okay, so it will be compressed, okay, by amount of K2 x1. So it started with K2 x1. Okay, however, the other end of your spring is able to move up, isn't it? So when your spring moves in the direction of x2, your compressional force will be reduced by K2 x2. Okay, why? Because the other end able to move. Of course, x1 and x2 is a two different displacements, not the same. So what happened is, when your spring K2 being compressed by x1, it will have the force K2 x1, but that compressional force will be reduced by the amount of displacement at the other end of your spring, which is K2 x2. So in total, force for your FS2 will be K2 x1 minus x2. Okay, so how to check which one minus which displacement minus which? You have to do your imagination, and you have to start with where is the external forces. In this case, your external forces happen at M1. So of course, your spring will be compressed with that external forces first, and then the other end of your spring will reduce the compressional force by K2 x2. So this is the total force of FS2. So I'm going to write here, number 2. FS2 is equals to K2 x1 minus x2. Okay, because the location of your damper okay, because of the location of your damper is it's next to your K2, and the situation is the same, isn't it? Because your damper will also have compression first. When your external force push your mass 1, damper will have compression first, okay, before the other end of your damper here reduce the compression. So this is the same as your spring. So for damper also, you will have force F damper is equal to, of course, force F for damper, it will be CD, isn't it? If you remember, for damper is CD x, okay, so for damper is C dx over dt. Okay, but in control, I'm not going to use dx over dt. I will use a d operator. So it's going to be C that d over dt will represent by a capital letter D, and then that is the x. So I'll do that representation of my damper, okay? Right? Okay, so in this case, the D operator is actually, D is representing d over dt, all right? Okay, so in this case of your damper, it's the same. The displacement FD, initially you have CD x1, okay, and then the other end of damper will reduce the compressional force by CD x2, okay. So then the total force for your damper FD will be CD x1 minus x2, which is very similar to your spring. Is that right? Okay, guys, if you have any question, okay, if I go too a bit too fast, you can come back and you can unmute and then tell something, all right? Because otherwise I can't hear you. All right. So number 3, force due to damper is going to be CD x1 minus x2. All right, then I have force due to mass. Mass is very easy because mass is a rigid body. So rigid body, it doesn't have any changes of displacement. Of course, when let's say this is a remote control here. When I push, can you see my remote control? Okay, so when I push this end, x1, x2 will be the same, isn't it? For rigid body, it is not the same as spring or a sponge or anything that can actually reduce the force. Okay, in this case, no. When I push here, displacement x1, okay, the other hand end here will also move with x1. Okay, so for mass, it will not have reduction of displacement, reduction of forces. So for mass, is very straightforward. Which displacement that move it? So for M1 is just, of course, for mass, the equation is force is equals to mass multiplied by acceleration, right? Let me just write down somewhere here. Force is equals to ma. I'm not going to use a because a is the mathematical equations of acceleration. I'm going to write in the differential equation. So F is equals to m d squared x over dt squared. Okay, and again, I'm going to change that d operator of d over dt is going to be m d capital letter D squared x. So that is the representation of mass, okay, for all masses that I'm going to use later on. Okay, so this is the representation of masses, right? So in case of FM1 is going to be mass 1, okay, multiplied by d operator 2 squared multiplied by x, which displacement, if you look at M1, it is actually, M1 here, okay, it is actually affected by displacement x1, and M2 here is reflected by displacement x2, okay. So FM1 is equals to M1 x1. Number 5, FM2 is equals to M2 d squared x2, okay. So for mass, it won't have x1 minus x2 or anything like that because mass is a rigid body. Okay, now I already have 5 equations. Now I'm going to do summation of forces. When I want to do summation of forces, I will look into my free body diagram with my kinetic diagram. Okay, I have two free body diagrams. I have 2 masses for my free body diagram. Okay, therefore I will have 2 equations. This is free body diagram. This is just now kinetic diagram. All right, so I'm going to equate them, isn't it? Okay, I'm going to equate the forces. So for mass 1, for the first body, I will have to assume going up as positive, okay, because this is going up. For force 1 is going to be, I'm going to assume mass 1 is going up. So I'll take going up as positive. So the summation of forces will be, summation of forces is of course equals to MA, which is, MA is what? Is the force due to the mass. Okay, so I'm going to have for equation 6, right? I'll take going up as positive, therefore force is a positive equation, and then Fs1 is negative, and then Fs2 is negative, and then FD is negative, minus FD is equals to the summation of forces is equals to FM1. Okay, which of course FM1 is MD squared X1. Alright, and then similarly I'll do for equation 7. For my summation of forces for M2, I will only have two forces going up, so both are positive. FD plus FS2 is equals to FM2. Okay, both of them is going up. So I have FS2 plus FD is equals to FM2. Okay, so these are your you've done the second part, which the third part, which are the derivation of all the mathematical equation representing your suspension system. All right, so you have your suspension system, and then these are the mathematics. So next, what to do next is to do the number 4, to draw the block diagram representing this system. This is the analytical way of modeling the system. Okay, so what I'm going to do is I'm going to draw the block diagram. I hope you still remember from your control classes how to draw the block diagram. Otherwise, you have to do a little bit of revision on how to do it. Okay, right now. So for the block diagram, I will start with input, which in this case just now, if you remember, we decided that input of the system is, I put here just now, input of the system is Ft, and then output of the system here is X2. The input is the external forces happen to the suspension system, and then the output of the block is going to be the one that I want to control, which is X2, isn't it? I want X2, the displacement just now, to remain on its steady state, on its fixed reference, even though the system is actually moving, the suspension system is moving up and down. All right, so the input is F, the output is X2. Okay, then to draw block diagram, okay, now the fourth part is to draw the block diagram. All right, so to draw the block diagram, you always start with the input of the system, and you will use all the mathematical equation until you find the output of the system. All right, so I repeat, you will always start with the input of the system, and then you will draw your block diagram using all the mathematical equations that you have until you find the output of your system. Okay, the output that you have decided just now. All right, in this case, you're going to start with Ft, and then you're going to draw until you find your output, which is X2. Okay, let me just recap on how to draw block diagram for those who forget. As simple as, for example, if I have force is equals to Kx, okay, a simple spring. This is just an example, okay, doesn't relate with my suspension system. So when I have this, I have to define what is the input and what is the output. In this case, block diagram will be just a block with input and with one output. Okay, inside the block is all the parameters. Okay, and outside the block, the input and the output here is your what? Variables. All right, so in this case, F and X are the variables because it can change with time, isn't it? And K here is your parameters. All right, so when you draw your block diagram for this problem, force is equals to Kx, all right, you need to decide which one is the input and which one is the output. Let's say if I decided input is X, output is F, okay, the block diagram, the transfer function that we're going to have is the equation of transfer function of your block is TF is transfer function, okay, is represented by output is equals to transfer function multiplied by input. Okay, so output is equals to transfer function multiplied by input. Therefore, in this case, if I decided that the output is f, then the input is x, then the transfer function must be k, isn't it? Because it actually reflects my mathematical equation earlier, isn't it? Okay, so the transfer function must be k. All right, so then my block diagram will look like this. Input is x, the block, then I have transfer function k inside, the output will be f. That's how you draw a simple block diagram. Let's say I decided differently. Let's say I decided output is x, input is f. Is it okay? Yeah, it's okay. It's quite straightforward. I can do that, right? However, I need to go back to my transfer function equation and rewrite this, isn't it? So my output is now x, my input is now f. So what do you think is my transfer function here? Okay, go back to this equation, right? Okay, you go back to that equation. So in order for you to have x is equals to something multiplied by f, of course the transfer function will be 1 over k. All right, the mathematics will remain the same. You just rearrange it so that it follow the equation of your transfer function. This is just a recap for those who don't remember, okay? But however, you need to do a little bit of your own revision if you don't remember this. Okay, so in this case, input will be f. Then I have a, sorry, this is k. I forgot to write just now. Okay, input will be f, and then the output will be x, and then the transfer function will be 1 over k. Okay, so this is the basic of on how to draw your block diagram. All right, so anyway, I'm gonna go back to our equation just now, and we're going to draw the block diagram of our suspension system. For your system, you're gonna have also summing point. So if you remember on summing point, it is actually all the signal that comes in, all right, addition or subtraction of the signal, and then one output should go out from your summing point. I will show you what while drawing it later on. Okay, so we have 7 equations. Let me just write it here so that we don't have to go up and down. Number 1 is fs1 is equals to k1x1. Number 2, fs2 is equals to k2 x1 minus x2. Okay, this one you have x1 minus x2, so you will have a summing point later on in your block. Number 3 is fd is equals to cd x1 minus x2. Number 4, you have your mass. Fm1 is equals to m1 d squared x1. And then number 5, Fm2, m2 d squared, that's x, okay, x2. Okay, number 6, you have your summation of equation from free body diagram just now. You have force minus fs1 minus fs2 minus fd equals to fm1. And then number 7, you have fs2 plus fd is equals to fm2. Okay, so you have all these mathematics, so we need to draw the block diagram. So I will start with, as I mentioned just now, start with the input of the equation. So this is the input here, isn't it? Okay, so I will start with that, and then I will end with output. I have x2 as my output. I will always start with equation that have my input. Okay, so in this case, I'm going to start with equation number 6. So you see equation number 6, I have f minus fs1 minus fs2 minus fd. These are all forces. Forces are variable. Okay, fm1 is also forces. Forces are variable. So variable, you don't, in this case, you don't have any parameters. So it means to say your system is just a summing point. It doesn't have block. So I'm going to have force as input. Then I will have all these minus fs1. In this is my summing point, okay? Minus fs2. And then maybe I put another block okay, another summing point, because otherwise it will be too many there. So I have minus FD, okay. So then this is the output is FM1, all right. So now, how to start with the, so I complete equation number 6, okay. So I don't, when you want to draw the block diagrams, when you've done one equation, you're gonna stop. You're not gonna you're not gonna repeat the equation again. Okay, so I might as well take it so that we remember that. Then I will start with FM1, because why? Because now the equation that I have here is FM1. So I need to then solve equation or draw block related to FM1. Okay, so in case of FM1s, let's have a look at FM1. Okay, FM1, I have two variables, which are FM1 and X1. That's my variable. Okay, and I have the rest are the parameters. So the rest of the parameter, it will go inside the block. All right, the variable will become input or output of the system. Okay, in this case, can you see that FM1, the arrowhead is already showing it as an output to the summing point. Therefore, it cannot be output anymore. It have to become input. Okay, it have to automatically become input to a block. Okay, so in this case, if the input is FM1 and then I decided the output is X1, why? Because of the equation of equation number 4, okay, then the transfer function will be 1 over M1D squared. Okay, 1 over M1D squared. It doesn't look nice. I'll redraw that. 1 over M1D squared. Okay, that's your X1. All right. Okay, now that you have solved that equation number 4, that's how it is. All right. So then what happened next is that once you have done, you get your X1 now as the output, isn't it? So when it become an output, it need to become an input. So what are the equations that have X1? I have several equations that have F1. I have here equation number 1, equation number 2, and equation number 3, all having X1, and I will choose the one with a minus, the one that have X1 minus X2. Why? Because it will involve a summing point. If I choose the first one, it is not a very wise decision, because later on my summing point will be at the bottom of my block. Okay, so I will choose either either equation number 2 or equation number 3. It doesn't matter which one. Okay, so in this case, let's say I decide to choose equation number 2. So for equation number 2, you look here. This is variables, this is variable, this is variables. All right. So in this case, those are your input and output. The only thing that you have is K2 as your parameter. So when you have K2 as your parameter, so you need to decide now, X1 is your input, all right? But you see here, X1, that it have minus, isn't it? So when you have minus, you need to put a summing point. So X1 is the input, X2 also is the input, okay, where the input, the total input is X1 minus X2. I don't know where that X2 will come from yet, but I'll draw the block first, then I'll find out where does it come from, all right? So I have X1 minus X2, then that is becoming the output of my summing point, which gonna be input to a block, okay? Then the final output of that block is FS2. All right, so inside this block, you look at this equation, you need to change that equation into the following the output equals to transfer function multiplied by input, remember? Okay, so we need to rewrite that equation. So your output now is so you don't need to rewrite the equation, it's already okay, isn't it? So the output is Fs2, the input is X1 minus X2, so the transfer function must be K2. Is that okay? Right? Okay, now next is your Fs2 here. Let me just put the fs2 here. fs2 is having it becoming an input now, isn't it? So the only you cannot do this equation of fs2 anymore, you see, because you've done it. Equation number 2, you've done it. So the next equation that have fs2 is this equation number 7. All right, so equation number 7. So equation number 7 says fs2 plus fd is equals to fm2. These are all variable. It doesn't have transfer function. It doesn't have parameters. So it means to say it doesn't have transfer function. It will not have a block. It only have a summing point. So fs2 plus fd. Okay, normally I put my plus or minus outside the summing point. But however, in control, you can also put it inside the summing point. I will show you later on in the class, okay? Right, so I have fs2 as positive signal, fd is a positive signal, the output here is fm2. Okay, that's all. So done. Equation number 7 is done. All right. Next, how to proceed with equation number 7. After that, you already have fm2, so you need to find the equation of fm2, which is equation number 5. So equation number 5, you have fm2 as your variable and x2 as your variable. Okay, so the only transfer function you have is m2d squared. So m2d squared have to be inside the block as your transfer function. Okay, in this case, fm2 is already an output to the summing point, therefore it need to become an input. Let me draw this nicely. This is fm2. Okay, so it need to become an input. Okay, input of what? Input of a block that have output of x2. All right, because that's the only variable left, isn't it? x2 is the only variable left for equation number 5. So fm2 is the input, x2 is the output. You need to follow this equation of transfer function here. Therefore, you need to rewrite the equation so that your transfer function, your equation is x2 equals to 1 over m2 d squared multiplied by your input, which is fm2. Okay, so when I rewrite that, automatically my transfer function become 1 over m2 d squared. Okay, let me try to get this written nicely. But I'm sure you're taking notes, right? This is m2 d squared. Okay, the output here is x2. I need to buy a bigger iPad because this is too small. The screen is too small. Oh, maybe I can try to cut this and then move it a little bit. Oops, can I do that? Yeah, I can move it a little bit here. Ah, nice. Okay, so let me write this nicely because it was not nice just now. So I have fm2 as input, and I have 1 over m2 d squared. Then the output is x2. All right. Okay, now see, I already start with my force as the input to the block, and I already end with the x2 as the output of my block. Okay, but however, you see there are some equation not yet being done, isn't it? I have equation number 1, equation number 3, and equation number, okay, that's the 2 equation that I have not done it. So I need to complete it. And also, you see there are some arrow going to the summing point, but we don't know where it comes from, isn't it? We need to complete that. That is what we call the loop of your block. Okay, so you need to complete those loops. Okay, so let's look at FD here. How to solve FD? FD is CD multiplied by x1 minus x2 for equation number 3 here. Okay, so I already have x1 minus x2, isn't it? This is x1 minus x2 here. Just now I've done it, so I'm not going to repeat that. Okay, I'm going to take that signal here. When I put a tab like that, I call that peak off point. So I'm going to put a peak off point at this x1 minus x2. I'm going to pick that signal. okay, make it as input to a block, okay, and that block is transfer function of CD, isn't it? Okay, so if I put CD in that block, so you see this input is x1 minus x2 multiplied by your transfer function CD, you're going to get FD. So that's how you complete the loop of your FD. Sorry, FD is not loop, it's a parallel system, it's a feed-forward system. So that's how you complete FD. All right. And then you see here, this is a summing point that require FD. Okay, so since you already have FD, you can just pick that signal FD here, take that signal, use pick off point, and then connect it to your FD. All right, so that's how it is. And then other signal, you already have it. For example, you have FS2, isn't it? So you can pick FS2 is here just now, isn't it? FS2, I can use another pick off point, put a dotted there as my pick off point, and then I can just take that as input to this FS2. Okay, and then what else? Oh, x2 here. See, I need x2 in this summing point. There's a summing point number 3 here. I need x2. So I'm going to take x2 from the end here, isn't it? The output here is x2, right? So I'm going to pick off the signal from my output and become x2 into this summing point. Okay. Lastly, I need my FS1. Okay, so FS1 here, you see there's a FS1 from the first summing point. It comes from X1. So I can pick signal from my X1 here. Okay, and it become input to a block, right? Input to a block. Why? Because X1 here is already output to one block. It cannot be output again. It have to be input. So it become input to this block to solve equation number 1. So if X1 is the input, of course the K1 is the transfer function, then FS1 is my output of that block. All right. So guys, these are the complete, okay, the complete block diagram for my suspension system. Wow, 1 hour. Is it okay for this one? Do you have any question for this? Can I open for questions? Anybody would like to ask questions?
No, doctor, thank you.
It's okay, right?
Okay.
Yes,
Okay.
Professor.
Yes.
Please, doctor. Can I ask why you started from equation number 6?
Okay, you start with input of your system just now. So when you define input, okay, we start by defining what is the input and output of the system, right? So we define the input of our system is F, isn't it?
Of course.
And the
Yes.
output is X2. So when you start with input, then when you look at this, all the equation just now, the F is only on equation number 6. That's why I start with equation number 6. Is that okay?
Yes. Thank you, doctor.
Okay. Any other questions, please? All right. I will share our PDF, these notes, and I will send it to you later on. Okay. For you to do revision, okay, and I will give you other block diagrams later on for you to do a little bit of exercise to, you know, fresh up your memory on this block diagram and on block diagram drawings, and also the mathematical system on mechanical system. Okay, so I'll give a different mechanical system later on so that you can have a try on your own how to draw the block diagrams. Okay, there's going to be one of the exercise for today. I will give it later after this class. Okay, so now class, when I mentioned just now, if you remember this problem, it was a suspension system, isn't it? The problem on suspension system. Okay, I mentioned that we need to control this block diagram that I have drawn is not the complete control system. This is only a block diagram to represent the plan of your suspension system as the plan. Okay, so when I do block diagram manipulation, I can then change when I want to control this system. Okay, when I want to control this system, it's completely different. What I'll do is I will take this whole block. How to do that? Let me just write this. I will take this whole block, okay, as one transfer function. Okay, that whole block we can do what we call block diagram manipulation, which is taught in your control system. Okay, so when you do block diagram manipulation, you're gonna get the overall transfer function of that whole plant. This is the plant on your of your suspension system, but you can represent it as one block with all the mathematics, all the equation inside that plant. All right, so maybe we can do it later on, not today, because it will take a lot of times. Okay, so what happened, that block is becoming input. Let me just draw this again. Okay, oops, oh yeah. Okay, that block is going to be input and output. So I will have F as the input of my system, and then X2 is the output of the system, and I can then just write the transfer function of the plant as GS. Okay, so this whole thing, whole block diagram that we have drawn for the last half an hour is going to be represented as one transfer function called GS. Okay, transfer function of the system. Okay, so there's no control yet. Okay, in this there's no control yet. It's just an input and output of the system. Okay, so how to design the controller? You remember just now for our system, what we want is we want to control X2, isn't it? Do you remember? We want to control X2. So therefore, X2, you need to set a reference. Okay, so when you set the reference for X2, you are giving that reference. Let's put it here. I'm going to give the desired input of your system is X2 with a reference signal. For example, I want my car to maintain at a level of 20 centimeter or 200 millimeter from above the ground. So no matter what happened to my wheel, my body of a car will remain the same. So maybe when I go and I drive through a hump and a hole, my wheel will move up and down, but the body of my car, I want it to remain the same, so that my family inside the car will be very, very stable, will be very comfortable, isn't it? There's no going up and down, isn't it? Like I'm driving a very expensive OD, for example, isn't it? So it will not move up and down because I'm gonna fix that as my reference. So X2 as my reference signal. Okay, what I want it to remain, maybe the input to that system reference signal maybe remain the same. Okay, I don't want it to go up and down. Okay, so I'll just put a constant value for my X2 as the overall input or the desired input of the control system. All right, then when I have this, I need to put a summing point, and then I'm going to compare that reference signal with the actual input of my output of my system. I'm going to compare the actual, when the car start responding, what is the actual X2 with the reference X2. Okay, so now this is becoming the actual output. Okay, but X2 is your desired output. What is the, and we call it input. Okay, or we can call it also desired output. What we want as our output. Okay, what we desire as the output of our system. All right, so then of course there will be error, isn't it? When we compare this, I put this as positive, this is negative. Okay, normally class, if you read some textbook on control, summing point is represented as either a circle with positive and negative depending on your equation outside the block, or sometimes it inside here. You will put positive here and negative here, isn't it? Okay, so it's representing x2 reference minus x2 actual. Okay, so there from there you get what you call error of your system. Okay, so let's say I can design a controller. This is where I want to put my, for example, a simple PID controller. Of course, it's not going to work, but I'm just going to put it anyway. PID controller there, for example. Okay, this is your controller. So, or maybe don't put PID, maybe just put transfer function called GC. This is the transfer function of controller. We will work on the controller later on, okay? All right. Then that controller is maybe giving signal to your system on how to make that force. You see, this is the force from your car just now, isn't it? Force from your wheel, isn't it? So how to make that force cancel? How can we cancel that force? So that force is now not the input to your system. It is actually the input to the system, but we normally call it that force just now, okay, from the block diagram. This is the disturbance of your system. Why? Why do you call it disturbance? Because if you don't have that force, your car will always remain the same, isn't it? It will have your reference. You don't need the controller. But because it is disturbing your system, okay, all right, so when it's disturbing your system, then it's actually move your car up and down. Then your actual x2 will now becoming different than your reference x2. Therefore, you start to have error. Okay, so the force that is actually forcing the wheel to go up and down just now is called the disturbance of your system. Okay, how do I cancel that disturbance? Okay, so from the basic, this is just an idea. So for example, if I have that force going up and down, isn't it? Like this. Okay, so if only I can find out what is the actuation force, maybe I can put an actuator to cancel that force from the disturbance in a way that antiphase the force, something like that. Okay, of course the total force will be zero, isn't it? The total force will be very minimum or almost zero. Then my actual output will be the same as my reference. Then I will not have any disturbance on my system, so the car doesn't goes up and down. Therefore, this reference, the actual output x2 will be the same as the reference x2. Do you agree with me? Okay, so let this the red color is coming from your actuator of your suspension system. Okay, so then this F is your now known as your disturbance. Okay, so this is the whole idea. This is the idea on cancelling the forces. So how to do that on your block? Okay, so I can put after my controller here, I can put an actuator to move my according to my controller's value of my controllers. Okay, so from the controller I can give some value. For example, if you read about a journal about MR damper, for example, so some expensive car is utilizing MR damper or force damper, so they can just represent put another damper at your system here and call that GA. GA is a transfer function. This is maybe, and we call it actuator. So the actuator can be another damper placed in between your suspension system just now, so that that damper will control your force. Okay, so hang on, let me just write here, so that the force from your actuator, if I put into a summing point, adding the force from your disturbance FD just now, this is FT just now from our equation, isn't it? Now it becoming disturbance. Okay, initially it's just a force from the road profile. Okay, so we call it disturbance now. So the total force, why my arrow doesn't look like an arrow? Okay, force due to actuator, maybe I write this as FA. Okay, and I add into my disturbance force, so I will get this one positive, this one positive, so I'll have a total force. Okay, so the total force to my system, I want that total force to be 0. Okay, F total is equals to F A plus F D. A is coming from the actuator, D is coming from the road profile. Okay, so if I can design such a controller here, GC, that can give value to my actuator, maybe I put a MR damper to my system, and then I come up with a controller that can give information to my actuator, so that the force coming out from my actuator is anti-facing my actual disturbance, then of course my total controller, my total force to my system just now, this is the suspension system just now, will be 0 or very minimum or very small. So when that very small, of course your system does not move so much, isn't it? It will actually now your X2 can be guaranteed that it will not move so much. When the total force is 0, of course X2 will remain the same on your suspension system. Okay, so this is an overall view of a control system. So this is a normal control system. It's not requiring you to do adaptive. Okay, so I will talk about why is it different just now. Okay, so this is the control system. Any questions so far for control system for the actuator?
Excuse me, Prof.
Yes.
Is that should be sensor in the feedback?
Of course, there will be sensor. Normally, you know, control people, they are very funny because when they draw block diagram, they just put one arrow, isn't it? So that feedback loop is actually consisting all your sensors. Okay, here,
Yes.
it's here. These all, oops, I want to put it blue color. I forgot to change the color. So yeah, here is where you put all your sensors, because of course you want to find out what is the actual vibration, or what is the actual X2 that you have, isn't it? So yeah, you put your sensors and all. Of course, even the controller is actually within your computerized controller. In the block diagram we put that way, but in if you talk about the actual implementation of it, these are all inside your computer. Okay, so these are all inside your computer. Okay, with all the instrumentation and all the sensors and all the controller, all the data acquisition system with digital analog converter and all, so many things here. So of course, when we draw block diagram, it looks very simple, but in reality it's not that simple, right? Okay, then the output of your data acquisition system coming from your transfer function of your controller will transmit the information to your actuator. Your actuator, guys, can be as simple as not as simple, maybe in between this mass just now, isn't it? This is the passive. Oops, I put differently. This is the passive. This is your damper just now. Okay, this is your spring. So this is the passive system, isn't it? Suspension system. So we can put one, maybe MR damper there. So that MR damper is your actuator. Okay, so the information from your controller, from GC, will tell your actuator how to produce the FA. What kind of force to be produced, either to move it up or move it down. Okay, so your this is an example of, for example, MR damper or any damper that you can put as actuator to your system. So your system with actual passive suspension system, when you undergo a road profile, you have your actuator here. So that actuator will move your up and down of your system, so that the total force for your reference signal X2 just now, you can refer to the reference X2. So the reference X2 will remain the same. Okay, let's put that as, maybe I put just now, I mentioned 20 centimeter. Is 20 centimeter okay? It's too low, isn't it? This is a lowered car. Maybe 50 centimeter or 40 centimeters. Okay, so this is the reference. So let's say we decided this to be 40 centimeter or 400 mm. So 40 centimeters above the ground. So it will remain the same at 40 centimeter above the ground. All right. Is that answering your questions?
Yes, Prof.
Any other questions?
Yes, pardon, doctor. The output of the X1, why return to enter in the diagram? No. Above, doctor. Above. Yes, this is.
This one?
Output X1, yes. Why return to parameter X1? K1, sorry.
Okay,
Enter
alright.
again, yeah.
You remember you have just now when we draw the block diagrams, okay, what happened is that you've done a lot of all the equation, but you have not done equation number 1, isn't it? It was not complete just now, isn't it? Okay, so when it's not complete, you need to complete it. When you have write down your mathematical equation, if you have 7 equation, you have to draw all 7 equation in your block. Okay, so just now the force Fs1 equals to K1x1, we have not drawn it. Okay, so we need to actually draw it as well. So, okay, so we need to put the parameter K1 inside your block. Okay, so in this case, I have already have x1 from the previous exercise, from the previous when we draw it. Let me just delete this first. Okay, so initially it was like that, isn't it? Okay,
Yes,
but
this
it was
is
not,
doctor. Yes, this doctor. Yes.
okay, so it means to say, you see that Fs1, you don't know where the Fs1 come from, isn't it? You need to define where the Fs1 come from, because in this case, your system only have two parameter variable coming from outside. One is the input, one is the output. It cannot have Fs1 also coming from the out
Doctor.
as input to the system.
Pardon, one parameter can one or two?
Or you can only have one input and one output.
Yes.
Okay, so in this case x1, so I need to complete the diagram, isn't it? So I pick, because I already have x1, I pick x1 becoming input to this block. Okay, and the output is Fs1. All right. Okay, so if I follow the input-output relationship, if input is x1, output is Fs1, then the transfer function must be K1. That's why. Is that all right? Does that answer the questions?
All right.
Okay, thank you. All right, any other question, guys? I'm recording this session. I will send the recorded session later on. So maybe you want to go through back, and then maybe because sometimes I talk too fast, so maybe if you watch the recorded session several times, it maybe makes sense. Okay. All right. Any other questions so far? It's quite straightforward, right? So this is how you want to draw the block diagram, is for you to actually model the system. What the main idea today is actually you want to model the system. Let me just go back to my slide. Let me stop sharing this and then share my slide again. Okay. Oops, sorry. Right, so in case of the suspension system just now, we already draw the block diagram representing the whole suspension system. But you remember that suspension system is just one subsystem of your car, your automotive. So the automotive is actually a massive construction of many block diagrams and many other systems put together. Okay, so for this is what we call the solution for modeling, the analytical way. So if you remember, I mentioned about analytical way just now, is splitting system into several subsystems whose the parameter are well known. Well known means you can write the mathematics of it. Okay, you can draw the mathematical equation, and then you can draw the block diagram of the system. Alright, the disadvantage is applicant dependent. So it means application dependent. Means it's different application, you need to redraw the block diagram. If it's talking about a furnace system, if it's talking about other mechanical system, of course you need to do it over and over again. Alright, so and also it's time consuming. You see, just now when we want to draw block diagram, it takes time, but of course when you have to do it, isn't it? And the model can be very complex as well. Okay, so that is the first modeling technique. The second one excuse me, the second one is using system identification. I have in this slide least squared, but I don't think I have enough time to explain to you. Maybe it's too much. for 1 day. So maybe I will record the least squared session and send to you later. Okay, so it's just I'm going to show you what does it mean by system identification. Okay, system identification is a program or a mathematical equation that when you draw the block, you don't need to draw the block. When you have a system, the model of a system is estimated. So rather than drawing the block diagram like what I've done just now, I'm just going to estimate the model of the system by assuming that the system is a black box. So I don't understand what is the mathematics. Okay, normally this is very, very useful when the mathematical equation of a system is unknown. If the mathematical equation of the system is known, it's better for you to write down the mathematical system. For example, suspension system just now. For suspension system is a well-known mathematics, so you can just draw the system using analytical modeling. But if the system is unknown, for example, a motion of your ship when it moves with wave, okay, how does the wave affect the motion of your ship? It's very unknown, isn't it? It's quite tricky, isn't it? Because it depends on the wave motion, it depends on the wind stream, and also you do not know how to write the mathematics of that. Even if you can write the mathematics, how can you connect between the wave motion and the ship model? So this is how an example on when you can rather than writing down the mathematics model of the system, you can use system identification. Okay. Okay, there are some system when you have the process or the model of the system, okay, some part of it can be written in the mathematical way, but there are some part of it you cannot represent it in the mathematical way. So we can use what we call a combination of both methods. We can have partly analytical modeling and partly system identification, and the combination of these is going to solve the whole process, for example. So when you model the process, okay, then you need to verify with the actual process. So in this case, once you have modeled the process using system identification and combining it with analytical model, you can then simulate the system and then verify the process if it's correct or not. If it's correct, then you can utilize the simulation to analysis and also design controller that can control the system. All right, so the basic idea to get the model of the system is because we want to design the controller to control the system. Okay, so this is maybe I'm going to go quickly on this. All right, for modeling a problem, okay, we want to know how can we identify a system. All right, so when we have a system just now, in case of suspension system just now, it's very straightforward. You have one input and one output, but not all system having as easy as that. Okay, even though it's quite complicated just now, but it's actually very easy. All right, some system have multiple input and multiple output, and some system have a lot of disturbances, not just one disturbance. It have a lot of disturbances. For example, if I want to do modeling of a face, okay, I want to have a pattern recognition of a facial recognition of a face, of a human face. Okay, so you can have a lot of input here, isn't it? You can have the height of nose, for example. You can have the color of skin as the input. You can have the distance between forehead and your chin, for example, as the input. So you can have a lot of input to the system, to the pattern recognition for your facial recognition. Okay, and then you can have multiple output as well. For example, you can have the output to be your face when you are sad, your face when you are happy. So you can have several output, not just one output. If you put one output for your face recognition, then you'll be in trouble, isn't it? One day you are happy, you can enter the lab because the facial recognition will look at you and then recognize you. But the next day you are not happy, or you forgot to shave your face and all, and then the lab will not open the door because the facial recognition doesn't allow you to do so. Okay, so this is the kind of activities, a kind of plan that needs some multiple input and multiple output. Of course, also with your angle. Sometimes when you put the face recognition system, when the person take your picture, it will take your picture from different angle. Why? Because maybe when you want to use it later on the system, your pictures is not straightforward 0 degree angle. Maybe you have a little bit of 10 degree here. Okay, so this also can be the output of your system for facial recognition. So in this case, you need to actually do the modeling. It's a bit difficult. It's very it cannot be right in terms of mathematical model, right? Okay, so in that kind of problem, we can have what we call parameter estimation. We can estimate the parameter, okay, by giving some input to the system and collect some output of the system, and then we can actually model the system using the input and the output of the system. We can model the system based on specific or standard mathematical model, and then we can predict the motion, okay, we can predict the output and then check if the predicted output is the same as the actual output, okay, so then you're going to get your prediction error. Based on that prediction error, we can then tune our model so that it can improve the previous prediction. Okay, so when you run this several times, when you give a lot of input, a lot of output to let the model study the relationship between input and output, then your prediction error will become less and less. And once it becomes zero or maybe very, very minimum, then your model can be accepted as the accurate model representing the system. So this is parameter estimation on your model. So your model will have parameters, then you need to estimate the parameters. Okay, so this is what we call parameter estimation. All right, between from input and output of the system. For example, what are the example of this? For example, you have a linear relationship or a linear equation on a system, okay, so you can apply a input to the system, output. I think you've done this many times last time during your experimental activities. You've done it many times. When you plot the graph, okay, so you model it as y equals to mx plus c, for example, for linear model, isn't it? Okay, so when you have y equals to mx plus c, can I write here? Oh, okay, never mind. Okay, so that is becoming a model of your system, linear model. So y is the output, x is your input, then you have c and also m. You can actually then redraw the model so that you can get the best output so that the error will be less and less, isn't it? So this is how you do it last time for linear system. So of course, for your master level, we're not going to do linear system. We're going to do more complicated system, all right, for system identification. Okay, so this is a typical application for system identification. We can use it to monitor the performance of a plant, okay, a very complicated, maybe petroleum, oil and gas plant. We want to monitor maybe the level of the level of liquid in every of these tower, for example. Okay, so this is you can also use for predicting what is the life cycle of certain performance of the system and all. Okay, so this is the kind of application. You want to do monitoring of the performance, so you want to predict the monitoring of the system. Okay, so for weather forecasting, I mentioned this several times just now. Okay, when you have to forecast what is coming up in the next 7 days, when in the next 1 month, you travel a lot, you need to know, you travel to other countries, you need to know what are the weather at that countries, isn't it, before you buy your before you pack your luggage, isn't it? You want to know if you're traveling is it winter or is it summer. Okay, so if you come to Malaysia, if you're in Malaysia, you want to know if it's winter. We don't have winter in Malaysia. Okay, so you need to wear proper attire, isn't it? Okay, so this is why you need some weather forecasting, maybe not 1 week, 2 weeks, maybe 1 year in advance, because you want to buy cheap flight ticket. Now is not a good time to mention about flight ticket, isn't it? Because flight doesn't work, isn't it? Okay, yeah, I have a lot of flight ticket that is gone to the drain now that we have this pandemic. Okay, but anyway, this is what you do. You plan ahead, 1 year ahead. So forecasting also can be done 1 year ahead. Okay, for example, what do you need to forecast? For example, the water distribution, the rain distribution. Okay, you need to forecast because you want to make sure the water supply in that river is always consistent, so that the water supply to the from the river to the house are adequate for the people, isn't it? So you need to forecast. So if if you know that certain time the water is going to be more, at certain time the water can be less, okay, you need to build maybe a water dam to reserve some of the water when the raining season. In Malaysia we have two seasons, raining season and drought season. So during the raining season you want to keep some of the water, so that when it's a dry season you want to utilize this water dam, so that the water supply sent to the houses are adequate for them. Okay, so how can we know about when is going to be a raining season and not? We can do some forecasting based on the previous 10 years of data, for example. Okay, this is this diagram pictures of a Tacoma Bridge, if I'm not mistaken. This one, Tacoma Bridge. What happened is that the bridge is built very good, suspension bridge. What happened is that it is actually being disturbed by turbulence, or not turbulence, by, I don't know.
Save project or save the system structure for project.
Sorry.
To save structure for the bridge.
Yeah, the structure of the bridge is actually being hit by
vibration,
maybe by simple vibration, but because it hit the turbulence apa ni, the unexpected frequency similar to the natural frequency of the bridge, so that the vibration become big, and it's actually collapse the whole vibration, the whole bridge collapse. Okay, so if you can predict initially what is the not predict, if you during the design of the bridge, if you know the natural frequency of the bridge, okay, so you can design a bridge so that it have some precaution or some safety factor at this natural frequency, or maybe at least some alarm system when some disturbances coming from anything, earthquake or anything. Okay, so you can have some alarm system saying that the bridge is now vibrating and it can be collapsing, so people should not cross the bridge. So these are kind of things, you know, you maybe you cannot stop the bridge from collapsing, but at least you can monitor, you can give some alarm system to tell the people that it is no longer safe to cross the bridge. Okay, so this is the why you need to do some estimation, some prediction, and some forecasting on the system. All right. Okay. I'm not going to go through so much anymore, because I know it's been too long for you in front of the computer now. Okay, so just for you to know, I already sent you this slide. Okay, so you can go through the slide, but I will talk about the parameter estimation. Okay, for the linear model we have all this, so I have all this jargon. Maybe you can look up what does it mean by arcs, arma, armax. This is for linear model. And then for the non-linear model, we have NARCs, NARMA, NARMAX. Maybe you can look up at all the value, all the information first. Okay, in the textbook, any control textbook will have them. Okay, when you do parameter estimation, this is very important. First, you want to model, you want to do the model selection, and then you want to design, or you want to decide what is the best model order. And then for the data measurement, is it analog or digital data suitable? And then you need to have a simple methodologies, maybe using simple least squared, generalized least squared, or maybe recursive least squared. Or maybe you want to use artificial intelligence, you want to use genetic algorithm, you want to use neural network, or you want to use particle swarm optimization and all. Okay, so you need to know what are the best methodologies for your system. Of course, when I do my parameter estimation, I will go as simple as possible first. Okay, before I do system identification, I will find out if the system can be derived mathematically. If it can be derived mathematically, then we can forget about system identification. We don't need system identification. Okay, but if the system can be derived mathematically, but the performance is not accurate, maybe there are some things that we are missing from the theoretical maths. Okay, so maybe we need to do system identification. Then we will use the simplest model by assuming the model is linear. The system, if it's linear or non-linear, is based on your knowledge. What do you know about the system? Okay, so if it's known to be linear, then you just use the simple arcs model, for example. Okay, I'll talk about this later on more, maybe in the recorded session, because guys, if you know that Thursday is a holiday here in Malaysia, okay, so it is Maulidur Rasul, so it's a day, a holiday for Malaysian. So what I'm going to do is, maybe I'm not going to have a class because I'm going to respect your day off also. Okay, so maybe I will record a session to complete this slide. There are only 14 slides, but there is a lot of things to talk about. Okay, so I will record a session maybe, and I will send you, if I cannot send it through e-learning, because I still have issues with my e-learning. If I cannot send it through e-learning, I will send it through WhatsApp or email. Okay.
Okay.
Right. I think that will be all for today. I'm going to talk. If I go to the next slide, I will talk more and more. I will never stop. Okay. So if you have any question about today's exercise, today's sessions, okay, please ask. If you don't have any question at the moment, you can ask later on as well. Okay, through WhatsApp or through. If I don't answer the WhatsApp, you can give me a call. Okay, because sometimes I'm quite busy, so I don't read the WhatsApp. So give me a call. All right. Okay. So if you don't have any question, I'm going to end the session today. Do you have any questions?
Excuse me, doctor. Yes, I have two questions, please.
Yes.
The question number one about the attendance. How can we take attendance? This one. And the question two about.
Sorry, go back to the question one. Can you take what? Sorry?
Attendance.
Attendance.
Yeah, attendance.
Why do you want to take attendance? You are not the lecturer. I'm the lecturer.
Just to ask, not to ask.
I'll
Just
take attendance.
okay. No, just this, because I thought at barcode. That's why.
A what? Sorry.
I thought at barcode same another subject. I thought that. That's one. Question two about, could you please give us exercise just to do it more time?
Okay, I will. Okay, about the attendance, actually, because the session is recorded, the first meeting, I don't take any attendance, but
Yeah.
because the session is recorded, so I know who's attending and who's not, and there are not
Thank
many
you.
of you. Okay, so I don't have any problem about attendance. I'll take the attendance, and
I got the idea. Okay, thank you.
knowing
Okay.
who you are and you are here is good enough.
Okay.
All right. Normally, guys, about the attendance. Okay. As we already discussed, we're going to actually stick with our class time, isn't it? 9 o'clock every Tuesday and Thursday. So I'm going to stick with that because I don't want to disturb your other classes. All right. Because I know at 11, maybe you have another class, right? So I'm going to stick with that schedule. For our friends who are in Sudan and in Iraq, I'm going to send the video recorded so they don't have to attend the classes, but I'm going to have a split session for discussion with them. All right. Maybe they have other questions beside what you have asked today. Okay, so I'm going to have a split session with them maybe later at night. I don't want to disturb all of you, so I'll just have a quick session with both of them because their time difference is only 1 hour each for them. Okay. So then for the attendance, actually I don't have any problem or any issues with attendance. Only thing is that if you're not performing well, later on, I will check back your attendance. Do you attend my class or not? This is just to reflect my my teaching. If I know that you are attending my class, but you're not doing well, so it's maybe something about my teaching. Okay, but if you're not doing well and then I check that you are not attending my class, then maybe I will stop you from going for the further in the class. Okay, maybe you will not be allowed to attend the final exam, for example, right? Because you are not attending classes. So as much as possible, please attend the class, all right? Because we can have you see my slide just now, only a few slides. So don't think that because I give you a slide means you don't have to attend my class. You see, only two, 3 slides, but there is a lot of discussion that can be done on that slides. Okay, so a lot of information. Okay, somebody asked in the WhatsApp group, what are the textbook that we use? You can find any. I don't want to fix with any textbook, because most of the textbook there are too much information, there is a lot. So I don't want to tell you these are the textbook to be used, okay, because it's the same. Any control textbook is actually for basic control, for you to refresh on your control. But there are one textbook that I'm using, adaptive control, but I'm not asking you to buy those books. No need to buy, because there's a lot of information on adaptive control online. You can use the online material as well. Okay, so I will suggest 1 or 2 textbook later on, but not for you to buy. If you can find it, if you want to borrow and read it, okay, no problem. All right, because we use a lot of other textbooks as well. Okay, because there are several topics here. We're going to talk about adaptive control. We're going to talk about system identification. We're going to talk about artificial intelligence. There are several topics. So there's no one textbook address all, except we write that textbooks later on. Okay. All right. So, Ayat, why are you not sleeping? You're supposed to sleep. What are you doing here? Okay, I hope all of you are doing well. Are you okay?
Yes, okay, no problem.
You cannot sleep, is it? Thinking that you have class?
I sleep with Malaysia and woke up with Iraq.
Okay. you are allowed to, you are excused from the class. It's okay. No, I don't mind if you're not here. It's okay. But anyway, if you're around, it's much better. But please go through the video as well, because maybe you're very, very tired. You look very sleepy as well. Okay.
Sleeping deprived. Ayat.
Right. So yes, I will give you some problems related to the mathematical equation just now. I will give you some problem, but maybe later in the afternoon, okay? Because I have other activities after this, right after this. So I'll give you later in the afternoon, okay? And I'll try as much as possible to put everything in the e-learning, because the e-learning, it doesn't work on my end. Maybe because of my setting of computer. I will try again and again. Okay, as soon as I put it, it will go hang on me. Okay, so anyway, so that will be, I'll stop recording now because I've talked